Hello everyone, welcome back. We were beginning to solve the numerical example of supersonic jet problem. We said that we have a P naught of 80 bar and M exit is 2.0, and for this particular condition we found that P critical 3 was 1.024 bar, which of course will be equal to the P exit at the end of the nozzle when it is fully expanded. So, I just said it is equal to P exit. Then we also did P critical 2 and we got a number 4.068 bar. Okay. And so we wanted to pick a case where there will be a over expanded jet. So, we said the value should be something in between these two. To not to have problems with Mach reflections at the center axis, we picked a case closer to this end, so that our shocks will be just clean crossing like an X. So, I picked up P back pressure of 1.5 bar. So, now our job came down to I have to find that particular angle beta, okay, for this shock, which will make sure that P back is the pressure out downstream of the shock and upstream is your P exit. This is what we have to find out, that particular. Did I make a mistake? Yeah, it is 4.608, not 068. Yeah, thank you for that. 608, that is the correct number. Okay. So, we were discussing last class and we said that theta beta m curve looks like this for any oblique shock for particular Mach number, and now we have to look for some solution reasonably close to that pressure, because it is not very far. 1.5 is somewhat close to 1.024, which means I am most likely going to be in this weak region, and so I have to guess some beta value inside this range, and we said that this value was 30 degrees. How do you know that? That is the sine inverse of 1 by 2, where 2 is our Mach number. That is your Mach angle, and so I want to guess some value inside here. If you go look at Mach 2 condition, this number will be around 63 or something, peak value. We won't worry about that. Currently, we will just look at numbers as something in between. Let us pick a value of beta of 40 degrees. I could pick 50, but I know the answer should be close to 30, so I am going to pick something closer for easy convergence. Okay. So, I am going to pick a value beta 50. Sorry, I said 40, not 50. We will pick a value of 40 degrees. If I pick a beta value, immediately I can find my m1 sin beta, that is the normal component for that particular oblique shock, which is what matters to find the P2 by P1 across the shock. So, I will find that, and I know my m1 value is 2, which is the exit Mach number at that end of the nozzle. So, m1 sin beta happens to be 1.286. I will take this number as my Mach number and go and look at normal shock tables. I will find that P2 by P1, or I will call it PB by P exit here. I will find PB by P exit, that happens to be 1.763. So, now I will find my P exit, multiply by P exit I will get PB, sorry, PB I will find, that number is 1.805. Of course, it is in bar. Okay. So, that is the number I am going to get there. I see that the pressure achieved by this oblique shock is higher than the PB we actually have, okay, which means the shock angle is too strong, it is too normal, right, it is more normal, normal is higher strength shock. So, you want to make it less angle, beta should be lesser. So, next value we will guess 35. I know 30 is no use, right, P2 by P1 will be 1 for 30. If P2 by P1 is 1, then my PB will be equal to 1.024, that is lesser. So, I want to pick a number in between 35. So, for this m1 sin beta is 1.147, and I go look at normal shock tables, again I gamma equal to 1.4 table, I get that value 1.368, and my pressure happens to be 1.401. So, I am close. Now, I know the answer is in between these two numbers and closer to the bottom number. I want 1.5. Okay. It is like 1/4 from here this way up. So, I will pick a number something close to that. 1/4 from here will be 1.25 added, I will just make it 37 degrees. We will try 37 degrees and see what happens. That 1.204, and the next number is 1.524, and so I am getting 1.561. So, now I see the answer is between 35 and 37. Logical thing to try 36. Number is 1.176, 1.447, 1.482. So, the actual answer is something in between these two, very close to 36 degrees. Okay. So, I tried this 36.2, okay. Just guess. I tried this. I know the answer should be closer to 1.48 than 1.56. Then I am getting 1.181, 1.461, and this is 1.496. I do not want to iterate any more than that. I stop there. Okay. Because my theta beta m curves which we have, we do not have so much accuracy in our theta values. When I go for beta values of this kind, typically we get numbers something like m equal to 2, m equal to 3, m equal to 4, like that, and the beta, the resolution typically is every 2 degrees, and I am thinking about 0.2 degrees here, which itself I cannot read from this kind of chart. Okay. So, I do not really have to go to this accuracy, I should be able to stop at 36 and say it is close to 36. I just went a little far, and when I wanted to find, I am going to say this is my beta value. Now, of course, the next thing I want to find is how much is the velocity deflection from here, how much did it turn by. Okay. So, I have to go find out that value from that chart, and I am getting that value to be 7 degrees. It is a rough estimate, I will put this approximately equal to sign there. Okay. It is just a rough estimate, I do not have resolution there to find this from the chart. Okay. So, now I will go do this whole analysis. I will go through that full oblique shock calculation for beta equal to this value and m1 equal to 2. So, my m1 sin beta is 1.181, m2 sin beta minus theta is 0.855. How did I get this number 0.855? Normal shock tables, looking at this number as the incoming shock, find out the outgoing shock, that should be the number put here, outgoing Mach number, and now I have to get the actual m2 out of that point. I know my beta and theta, I can get m2, that m2 value happens to be 1.753, which means I started with m1 equal to 2 and my m2 happens to be 1.753 after my oblique shock. We have done this kind of calculations already, so I am just going a little faster, and also it involves a lot of iterations, so I just went a little fast. Now, I want to go a little further into the jet. I have this particular case. Now, I know that I have a shock which is having an angle 36.2 degrees, which is turning the flow by only 7 degrees, very small angle change, that is all it is turning by. That angle change is 7 degrees, that is all it is doing. I know my pressure here now, this is region 1, region 2, I know the pressure there, which is our P2, which happens to be equal to PB, back pressure. I want to find region 3. How will I find region 3? I just have to go for, I know my Mach 2 there, I have a shock which will turn it back to parallel to the axis. What will be that angle? Again 7 degrees. Okay. So, in this case I am given theta equal to 7 degrees as the input and M2 is given to be 1.753. Now, I have to find M3 here. Again oblique shock, we have to just go through the whole process. This is the easier one because now I can go look at the theta beta m chart for 7 degrees and 1.75. I will just interpolate between two curves and I will get to a number, and that happens to be beta approximately equal to 41 degrees. Approximately equal to 41 degrees. Now, I want to be very clear about what this 41 degree means really. I have a flow with respect to horizontal having 7 degrees. This is the flow direction and my Mach number here is M2 equal to 1.753, and with respect to this flow vector direction I have a shock which is 41 degrees. Remember, the beta is always with respect to the streamline direction. From there it is 41 degrees. I have to draw it such that it is with respect to horizontal some value. Let me find that number from here. How will I find that? What is this angle? Same as this angle, right? It is parallel lines, one line cutting through. I believe I did this geometry stuff long back in 6th grade, 7th grade, somewhere there. So, it is 7 degrees there, total is 41, this part is 7 degrees. So, the remaining is your answer 34 degrees. Okay. So, actually if I want to draw the shock here, this angle is only 34 degrees, but what the flow sees is 41 degrees. Okay. Flow is seeing 41 degrees. So, now I just have to go and find pressure here P3. Again simple stuff, I just have to find M2. I will put beta 2 here because this is the second shock. Okay. M2 sin beta 2, that value is 1.150. Okay. This will from normal shock tables give me P3 by P2, or I will call it PB, both are same, P2 equal to PB anyway. That value coming from this particular Mach number normal shock tables 1.4 gamma 1.376. Since I know my PB, I immediately get my P3, it is 2.064 bar. This is the pressure at that point. We know that my outside pressure, back pressure here is 1.5 bar. Pressure in the region 1 or at the exit of the nozzle was 1.024 bar. From here it went up by 0.5 bar more. From there it again went up by 0.5 bar more, right? 1.5 became 2.0, again 0.5 bar more it went up. Okay. And I want to continue the calculation, so I have to find out the Mach number at 3. M3 sin beta minus theta, beta 2 minus theta 2, again from the same normal shock tables I will get this information also, and that is 0.875, which tells me that my Mach number at 3 is 1.565. That is, I started with Mach number 2, after the first shock it became 1.753, after the second shock it became 1.565. Those are our numbers currently. Now, we want to continue the calculation even past this point. Now, I know my dotted line, if I extend for my jet boundary, when the shock reaches there, after that there has to be some expansion fan here such that the pressure in this region 4 is same as my back pressure, the outside pressure. So, from 3 to 4 I need to have expansion fan. Okay. Simple calculation after that. We know expansion fans are easier to calculate. I have my M3 to be 1.565, which gives me my nu 3 to be Prandtl-Meyer angle, nu 3 13.825 degrees. I am going to look at pressure at 3 2.064 and I want to find the final Mach number such that the pressure will be equal there. How will I find the Mach number from knowing the pressure? I have to say that that region is isentropic. If I have to say that region is isentropic, but I have gone through two shocks in the middle, it cannot be the same P naught as before. I have to find the local P naught. How will I find local P naught? I know the pressure and I know the Mach number. Okay. So, I have this pressure and I know the Mach number M3 there. From this, I will get my P naught 3 as 8.339 bar. Now, you can see from 80 bar it came down to 8.339 bar finally. Okay, that is what you are having at the end. We started with 80 bar P naught. Okay. Now, we continue from here. I know that across this expansion isentropic relation. So, P naught 3 is equal to P naught 4. Now, I know P4. If I know P4, then I know P4 by P naught 4. Okay. P4 by P naught 4. P4 is 1.5 bar divided by P naught 4 8.339. Okay. This value happens to be 0.180. So, now I will go to isentropic tables, isentropic compressible flow tables for gamma equal to 1.4. This is going to give me a Mach number at 4 as 1.78. It's going to give me a Mach number at 4 as 1.78. Okay. How much did it turn the flow by? How will I find that? Again, I have to find Prandtl-Meyer angle here. So, I will find nu 4 for that Mach number, that happens to be 20 degrees, 146 degrees. This is the number I have there, 20.146 degrees. Okay. So, now I can find out what is my actual change in angle, delta nu equal to delta theta, that is our Prandtl-Meyer expansion. So, I am going to say my delta theta equal to delta nu equal to 20.146 minus 13 point something, 13.825. Okay. Which happens to be 6.32 degrees. Okay. You are having around 6.32 degrees there. Okay. So, if I draw my picture beyond that point, initially this turning angle was 7 degrees. Now, I am turning lesser 6 degrees. Okay, it is not turning by the same amount, it is turning lesser 6 degrees. And this expansion fan goes beyond that, after that we know. So, I have solved for region 1, region 2, region 3, region 4. Now, I want to go to region 5. I want to go and solve region 5 next. How will I solve region 5? It is experiencing an expansion fan started from here with this particular pressure condition as the main information given by the expansion fan, 3 to 4. Which means it will operate with the same delta nu and the same delta theta, okay, because it is a symmetric system. If this pressure is different from that pressure, then it will do crazy things. Currently, we are taking it as symmetric system. So, I will use the same delta nu here again, which will mean that my angle of 6.32 up will come back to 0 again. Okay. So, it will turn back to 0 at that point. Okay. So, my delta nu is again equal to the same value 6.32. This implies that my nu 5, should it increase or decrease nu? from 4 to 5. Nu will decrease. Why? I am going to ask why even if you said increase. Is it compressing from here to here? 4 to 5, it is expanding because it is experiencing this expansion wave. Okay. From here to here, it is still expanding. It is experiencing an expansion wave. So, actually what should happen to my nu? Mach number increases. So, what happens to nu? It is a monotonic function, it is going to go the same direction, it is going to increase. Okay. So, I am going to say this will further increase. So, my nu should be the previous nu for 20.146 plus this 6.32. Okay. So, I am getting a number 26.466 degrees, 26.466 degrees. Okay. Now, I want to find P5. Okay. For that I need M5, which is easy to do, right? From Prandtl-Meyer angle I can just go to my Prandtl-Meyer function tables and get to a Mach number. Mach number happens to be 2.00, okay, 2.00, which means my P5 by P04 and P05 are the same again. Okay, I will put P05 here, P03, P04, P05 all are the same because these processes are all isentropic processes, P0 does not change. Okay. So, I can find this ratio for this Mach 2 condition is 0.128 and that is going to give me my P5 as 1.067 bar. Okay. So, have you ever seen this number before? Last class when we were solving this P critical 3, we got this exact same number 0.128. Why? We were looking for P by P0 for m equal to 2. One more thing to notice, we started with m equal to 2, we ended with m equal to 2. Okay? That is how it just keeps going, going to go up and down across there. Ideally, I should get back to 0.24. I did not get 0.24, I got 1.067. This is because of all those round off errors I had and accuracy in interpolation and all those problems will be there. Okay. Ideally, it will just go up and down across this. If I solve for one more cell exactly, it should go through the exact same process again. Okay. But after this point, it is more difficult to solve the problem. So, we will currently stop at this stage. This itself is too much for this particular course. If I think about it, it's an undergraduate course, I don't need to solve up to this point. I just thought let us go a little more beyond any other book. So, we can solve all the way up to one full cell of my expansion compression cell. Okay. So, we will solve at this point, we will not go beyond this because after this what I have to do is find out the strength of these compression waves and tell me where it is going to meet and finally form an oblique shock. That region is a very non-linear region and it is not easy to explain it to people right now. So, we will avoid this whole thing. If I do this, I will have to explain 5 classes, we will ignore that for now, it is not worth it. Okay. So, this the same process I can follow if I want a under expanded jet, which will start like this. Exit pressure will be like 3, condition 3. From here I will just go and I will suddenly say I cannot go past this point currently. I do not know how to solve for compression waves coming together and forming shock. We will leave it there for now. Yes.
We started with an 80 bar P0. How will you get 0.1024?
It is not 0.1, okay, we started with an 80 bar P0. Or did I make a mistake somewhere?
Yes, sir. Because here P04 is 8.33 and you are getting 0.1067. So it should be 8.
0.1 of this, maybe I did 8. Okay, so it looks like I did 8 bar and not 80 bar. Okay, maybe I made a calculation mistake somewhere. Okay. If that is 8 bar, then I want to see the other P0. Other P0 is going beyond 8, it cannot increase. I don't like that. So, I am not sure of this part right now, maybe I will go check again. Okay. 80 into 0.1 is 8, should be more than that. So, I have made a mistake somewhere, 1.024 does not seem to be right.
If you multiply 0.128 into 8, you will get 1.024.
You will get 1.024. Okay, so I have used 8 only, it looks like. Then how did I get a P naught more than this value? That is my next question. It should not be going beyond that. It is possible that I had made some calculation mistake somewhere. Let us assume that this is 8 bar for it to give this. It looks like 0.128 into 8 will give me 1. Yeah, 0.125 into 8 is 1. So yeah, it is close. So I agree. Most likely I used 8 bar instead of 80 bar. I made a mistake somewhere in my calculations. Okay. So from here I have come all the way up to here, and when I find my P naught 3 here, this looks like it is more than my initial P naught. That can never happen. Okay. So most likely somewhere along the way my beta approximations are hurting me. Okay. I have approximated it to 41. I have approximated the previous one 36.2. Where is it? Somewhere here it is 36.2. These kind of approximations are hurting me, and I have used theta or approximately 7. If I used 6.5, maybe it would have been better. I do not know right now what it is exactly. I did not go through this from my numerical code, I just used my charts, and so it is doing this kind of result. Okay. If I go and use numerical codes, probably I will get a little better result than this. I wanted to do it as if you guys can sit and solve in your rooms. So I used only whatever equipment you are having access to, and that comes out to be some number like this. And that is the reason I think most likely it is having a huge error, 8.339. Should actually be slightly less than 8, because each oblique shock will decrease the P naught by a small amount. I was wondering why it was dropping from 80 to 8. It cannot drop from 80 to 8. 8 to slightly less than 8 is what I expect. Maybe it should be 7.9, 7.8 kind of number. Okay. But because of these small errors, it is blowing up to some higher number currently. Yeah, I have rounded off the wrong direction. Okay. So when you are getting results like this, of course you have to now think about whether your calculations are accurate enough. Now you can say that your error band is really wide. Okay, you are getting results more than what is possible theoretically. Okay. So that is not possible to have happen ever. There is some error somewhere in that. Okay. And it is most likely because I approximated beta from looking at a chart which does not have so much resolution. My grid levels are like 2 degrees. I am resolving it into 0.2 degrees, 0.5 degrees kind of numbers. Not very good. That is where we had problems. Okay. Now I will stop jet discussion right there. All this time we did not think about viscosity in my gas, and I said that if I have viscosity, my jet, I have a picture here, so I will just use this. My jet boundary is something like this, and then it is going out like this, and then it is turning like this, and I said that it will go back down, it will go back up, again have the same cell structure. This whole structure keeps repeating, and I said it will repeat forever. How many ever cells like this? But if I have viscosity present, then this particular line along which the fluid is going, it has a fluid element below and it has a fluid element above. We know that fluid element at 2 is moving with whatever velocity corresponding to Mach number 2, okay, some value. It will be something pretty high, it is not going to be very small, while the outside is supposed to be stagnant gas just sitting idle. Okay. If that is the case, there is going to be a very high velocity gradient at that point. If there is such a high velocity gradient at that point, you can now immediately think about vorticity being present there. Vorticity is curl of del cross of V vector. Okay. So immediately I can now tell that there is a non-zero vorticity present there. In real life, if there is concentrated vorticity present somewhere, immediately viscosity factor will come in and distribute this vorticity equally all over the place. It is like you put a drop of ink in water, immediately it diffuses out to all the regions, finally you do not see any ink in water. The whole water is having all the ink dispersed everywhere equally. Till that time the diffusion happens. Similarly here viscosity diffuses the vorticity. Okay. The only place where you will see serious amount of vorticity is this edge, jet boundary alone. So you are going to have that special case called a shear layer. There is that one layer of fluid elements where you are going to have very high concentration of vorticity distributed along that line. Okay. And because of that, you are going to have viscosity in real life. Now I am no more in my ideal gas dynamics world. I am trying to include my viscosity in my gas dynamics. If I include that, then you will start having some momentum mixing happening across this region. I do not want to go disturb this picture anymore, we will just go a separate picture. This has nothing to do with compressibility anymore, I will just say it is just fluid mechanics. Viscosity does not care about really so much of compressibility. Viscosity is just something that worries about high concentration of vorticity somewhere and low concentration of vorticity some other place. That is not liked by viscosity. Think about it that way. One place very high vorticity concentration, other place there is no vorticity. Immediately vorticity will be taken from one point and given to the other point. It wants to make everywhere equal vorticity, which will eventually come down to everywhere equal velocity distribution. If there is any velocity gradient, there is some vorticity that place. Okay. That is what we are trying to achieve finally, that is what it will end up with as a final situation. Okay. That is the job of viscosity in nature. Okay. It is diffusing velocity differences or momentum differences among fluid elements of different layers, that is its job. So, if I look at a simple problem in fluid mechanics, ideally I should not be teaching this here, it is fluid mechanics course. Okay. I am supposed to be teaching only compressible flows, but I will anyway give you this so that you have that background when I start talking about supersonic compressible shear layers. Okay. If I have this velocity as something high, this is my velocity profile there, and this velocity being something low, and these two fluid elements meet when it comes out, and I am assuming that the plate is extremely thin compared to the dimensions I am interested in, very thin plate, I do not need to worry about the thickness of the plate. When it comes out at this point, I am going to still have the same velocity profile. If I think about vorticity in this region, there is no vorticity at all in this region, because all the velocities are exactly the same, del cross will become 0. Same thing on that side, except for that one line, the midpoint, the center line, that will be the only region where you will have non-zero del cross V. Okay. That is where you are going to have vorticity distributed, and all the fluid elements are going that way, which means I am going to have overall some convection of this vorticity distribution as it is going that way. Okay. While it is getting convected, viscosity comes into play and it wants to take that vorticity and distribute it every direction, up and down, all the directions. Every other place it is 0, only one guy is having all the vorticity, viscosity does not like it. So, it will just take it from that person, give it to the next person, immediate next person, and it just diffuses out from there, and everybody eventually has same amount of vorticity. If there are so many fluid elements, they will all have almost 0 vorticity, it goes till there. Okay. Now, immediately some distance downstream, I will draw a dotted line going slightly downward, we will come back to that later. I will have my velocity profile looking something like this. Far away the values are same as before, even here far away the velocity values are same as before, but now there is a whole bunch of fluid elements which have a velocity gradient. Okay. Of course, still the highest velocity gradient is at the center line, that is what it is still. Okay. But I have drawn that the center line is dipping slightly. Okay. We will worry about that later. I am currently assuming that the pressure for the fluid above and fluid below are the same. That is typically the way people think about shear layers. When they think about shear layers, they are going to think about pressures are the same, static pressures are the same. Okay. Now, eventually it is going to look something like this, and in the middle the velocity profile is changing. If you think about it, at the center typically it will be half the value or the average between that value and this value, it will be the midpoint, okay, typically. And if I go further down, there will be another region where it will be far away, it is still the same, far away it is still the same, but everywhere else it is having that vorticity. So, it is going to look something like this. it has distributed much more uniformly. Okay. Now, if I think about drawing a boundary for these things, I have to define something as my boundary. What do we do in boundary layer? We will tell that at the edge the velocity is same as far away. I will use the same concept here. When I look at far away on the top, that value is same as some value here. So, I am going to call that my edge. That point is my edge, which means that corresponds to this location here in physical space. This is just a profile, remember. Okay. And similarly, when far away here it is some value, and as I come closer it is deviating and going away at some point. That point I will call as my edge again. I have marked 2 points. Now, I will again go and do the same thing for the next profile at some other downstream location, somewhere far away out here, and out there it is somewhere there, let us say. It is all only schematic. I may not be going the same growth rate if you are interested in that. Okay. What will it be at this first point? They are both at the same location, they are merging, okay, because at that point everywhere the velocities are the same. From the top they are all the same, just when it is 1 point above, same thing 1 point below, everything is the same as below. So, it will be almost that point, both the x's will be meeting at that point. So, now I will draw a dotted line through all this, dashed line through all this, and similarly here. This particular region or the band of fluid elements I am considering is the only region where viscous diffusion or vorticity distribution, redistribution is happening. Okay. Outside this I am going to say the velocity gradients are almost 0, same thing below, almost 0 velocity gradients. So, there is no vorticity. Okay. So, this particular region is called the region of shear forces or the shear layer. This layer is the layer in between the 2 regions where there is not much of viscous forces. So, this inside in between region is called the shear layer. And if you go do more of a fluid mechanics course, you will start seeing that. Now, I will go for a different picture. I will draw a very thin splitter plate, and I am going to draw a more realistic shear layer growth that looks more like this. It will not be typically that. Okay. Oh, I wanted to talk about this going down dotted line. Typically, when we meet the pressures the same, the velocities are different, the P naughts for the top and bottom are the different values. Which one is higher? Upper one is higher because it is moving at a higher velocity for the same static. So, it has more energy. So, eventually it so happens that it starts pushing it down. So, the dotted line is the actual boundary between the 2 fluid particles. Let us say the top is oxygen, bottom is nitrogen. This line will be the line separating nitrogen and oxygen. I am still assuming that there is no species diffusion across that. Okay. Ideally, every diffusion happens across that. In real life, diffusion always happens. Okay. Diffusion is a natural process to make things equal everywhere. Okay. Now, if I look at a case like this, if my shear is not very strong, that is my delta V across these 2 layers, the top and bottom, the velocity difference, if it is not very high, then it will just be growing like this with velocity profiles just going simply like this. But if my strength of the shear is higher and higher, that is I am saying the top is moving much faster than the bottom. If I pick such a case, then I will have a situation where the strength of vorticity is so high that there will be some nonlinearities coming in fluid mechanics. Vortex roll up will start happening. You would have seen this in so many places. I am just going to draw this. These are nice pictures I can draw. You would have seen this in so many places. Fluid mechanics typically, you will see something like this. What is really happening is I am assuming the top is going faster, bottom is going slower. That is my assumption. Otherwise, it will not be turning down like this. Otherwise, it will just be a flipped up image. It will just go turn the other way. If this is bottom is going faster, it is going to have something like this. Now, I will tell you the main thing about this compressible shear layers. The same thing happens in compressible flows also. Viscosity does not care about compressibility. They are independent aspects of nature. They don't want to worry about each other. Okay. There will be a nonlinear effect if the things are too strong. We won't worry about that part right now. All I know is this can be independently thought about without worrying about compressibility effects as of now. I can tell you that this kind of roll up will happen if there is enough difference between the velocities to begin with. Okay. If the velocity difference is not too high, then I will draw another picture. It will still grow like this, but if I see that particular center line like whatever I have drawn, here it will just be something like this. It will just do this, just oscillate. It hasn't rolled up yet. It is just beginning to become unstable. Okay. If they are almost close to each other, not much of shear there, not much of shear layer there, the shear layer growth will also be really small and all that will go much slower. I just talked about simple shear layers right now. We will now think about compressible shear layers, and particularly I want to talk about these cases where large scale structures are formed. We will pick such a case, that is I am going to say one is going extremely fast compared to the other. Then I am going to form these large scale structures, typically some rotating eddy like structures. Okay. They are just going to be rotating as they are moving forward. When this one moves forward to become this, there will be one more coming from here to form something like this, and it just replaces every now and then. There is a particular rate at which it is going to be shed. Okay. There is so much to it, we won't talk about all that here currently. Now people wanted to understand this in compressible shear layers. Something like this, and I am going to say that is my shear layer, and I am saying that it is having some large scale structures that are growing as they go out, and the vorticity strength will keep on decreasing for all of this because it is spreading out more. Okay. It is not going to be rotating as fast as the first one. Anyways, when something like this happens, people started discussing, okay, I have a Mach number there. What will happen because of such a structure moving inside my high Mach number flow? That is how they started thinking about it. And then they realized there is another velocity here, so there is another Mach number here. By the way, the temperatures need not be equal here and above, so I will call it A1, A2, and I will put a M1 and M2, which of course means that I am going to have a U2 here and a U1 here, velocities. And I know P1 equal to P2, that is the only thing I can tell right now. I have some things like this. Now they started giving one velocity to this eddy or the large scale structure. They called it the UC, convective velocity. Okay. And based on that they started discussing things. They are going to say that U1 is some high value, U2 is some low value, UC is some intermediate value. Okay, because that is caused by these two differences, it has to be something in the middle, which you know from your velocity profiles also that this value will be roughly close to the middle average of these two values. Okay. So they started defining things like relative velocity of the fluid with respect to this structure. How will I find that? U1 minus UC. And I want something like Mach number to figure out whether there is going to be compressibility effects on this. So I will divide this difference divided by that particular speed of sound which matters for the top, divide by A1. Okay. I will call this MC1. Okay. Similarly, I can get a MC2 for the bottom structure as UC minus U2 divided by A2. I can get this also. Another definition, equivalent stuff. If I think about it, UC is more than U2. So if I look at it, there are these structures moving at velocity UC roughly, and the supersonic flow is going faster than that. So what will it cause? It is like some object is moving with some velocity and the other one is moving much faster, and we are in a compressible fluid. It will form a shock, right? It should form a shock in front of this somewhere here. Or if you think about it, I will just take one particular structure like this, I will draw that picture alone, something like this, and I know the velocity here is u1 minus uc. If I sit on this structure, it will look like u1 minus uc is the velocity here, and the Mach number corresponding to that will be this divided by a1. Now that is the Mach number of the flow here, and what will happen, it is like flow around an airfoil or something, some such object, right. It wants to go around this. So it is going to see set of compression waves here. Of course, they can come together to form a shock later. After that, it is seeing this turning, right, that is the induced velocity because of this vortex rotation also. So they will suddenly start seeing expansion fronts here, and immediately after that it is seeing a point where it cannot go anymore, this line. Why can't it go anymore? The next guy is sending fluid this way in, while this guy is sending fluid out this way. They are going to find an intermediate locally, something like a stagnation point there. It is not really stagnation point, with respect to these two structures it is like a stagnation point. Okay. Overall it is also having a convective velocity uc, which we have neglected, we have removed, so we can see this particular thing happening here. Okay. So what will happen, it is expanding, becoming higher velocity, and suddenly it has to stop. So if it has to stop, there has to be a shock again sitting there, so that it will immediately turn out and go out that way, and then the whole procedure starts again. It is again seeing things, there will be expansion, compression, initially compression and then expansion, and then another shock, all that kind of stuff will start happening there. This whole structure keeps repeating like this. Okay. Same thing on the back, on the bottom. If I look at the bottom side, I am going to say the velocity here is, I will just draw this as u2 as the velocity here, this is travelling at uc. So if I look at this, it looks as if I have a body that is shaped like this, which is travelling in a velocity u equal to 0 flow medium with a velocity equivalent to uc minus u2, okay, equivalent to this. Okay, it is as if I sit on this fluid, which is actually travelling at u2 velocity, if I sit on that fluid, I will see that this structure is travelling faster than it, which means it is like aircraft travelling in supersonic flow this way. Now what will happen, this is a body going like this, it is going to start forming shocks here, set of compression waves forming shocks, and then after that the body turns around, there will be expansion, and then the next shock, and then a set of compression waves again forming much stronger shock. This whole sequence starts happening here. If you ever happen to experience a shear layer in supersonic flow, you will start seeing these kind of waves. I am drawing it as if they are very strong, this decided by what is the actual difference between these. Okay, it is decided by what is the actual difference between these. Okay. If the difference is very large, then you will start seeing that these waves are not insignificant, these waves are not very significant, they become more and more insignificant. Okay. This is how your shear layer structure happens. So if I look at the whole thing, we will see, if we have a high speed camera, we will start seeing this on the top and this on the bottom all together on here. So I will just draw all of them together, shock, expansion, shock, the whole thing together forms a shock, and then expansion again, expansion will be more higher angle like this, and then there will be a shock, and again a bunch of compression waves going and connecting with that, and the next expansion starting here. On the bottom, this fluid is going faster than the outside, so there will be a shock, set of compression waves, and then a whole bunch of expansion waves, and then another shock, and the structure repeats like this. Shock, set of compression waves, and this structure repeats. If I ever have a high speed camera, I will remove this thing which is confusing. I will have this whole thing happening there. If I have a high speed camera and I watch this, I will see that there will be a set of compression waves which are just moving like a train, one after the other as it goes downstream, and this keeps on happening. And the same thing on the bottom, it will be just offset by a small amount and it will be going along with the structure again following this. Okay. This is the way the shear layer structure happens. Okay. We can discuss more about this. I can tell you that the pressure has to match at this point, and because of that you get a pressure matching condition at this point. We can talk a lot more about this, and they came up with a single convective Mach number using these two definitions, and that happens to be u1 minus u2 divided by a1 plus a2. Okay. It becomes this. There is just a little bit more, so I will just go this 2 minutes and stop after that. Okay. So, they found a convective Mach number based on this. Okay. Actually, it is based on these two formulae plus pressure matching condition. I can get to a formula simple enough if my gas is the same top and bottom. I can get to such a thing. Now, people started discussing this particular function, and they said that if this number is less than 0.5, then I am having only these structures, only two dimensional structures. I am assuming that this thing extends all the way out and into the board fully, just two dimensional flow field. But when this goes beyond 0.5, this two dimensional structure starts to break down and becomes three dimensional. If you want to think about it from fluid mechanics point of view, the velocity difference is so high. When I say this number is high, u1 minus u2 is very high, which means my vorticity is very strong, and vortex breakdown occurs. It is no more just a 2D vortex, it just breaks down and becomes streamwise vortices, and those streamwise vortices cause lot more mixing. If it is streamwise vortices, then there will be like rotation like this as they are going, and the next one will be rotating the other way as it is going, and the next one will be rotating counterclockwise as it is going, clockwise counterclockwise when I look from the front along the flow field. Okay. This is going to help you in mixing. This is what they study as mixing layer in supersonic flows. Okay. This is going to take this bottom fluid up and the top fluid down and just mixes. As it is, you can see that it is doing that by taking this fluid down into here, and this fluid has gone into that gap. But it is much more if I go for higher convective Mach numbers, where it will go three dimensional structures. Okay. And there are special research papers where they do this, and the recent paper I have experienced was 2003. Yeah. Anyways, we will stop at this point. Next class onwards we will go for non-isentropic gas dynamics. Okay. Any other questions you have? See you people next class.